Welcome to the Walton Pi. Today we're going to go through a test review that's going to cover L'Hopital's rule, optimization problems, Newton's method, sigma notation for sums. We're going to talk about finding area under curves, definite integrals, and the fundamental theorem of calculus. So to get started, let's go over L'Hopital's rule. So first off, what is L'Hopital's rule? So L'Hopital's rule, this is a way that we can be able to evaluate certain types of limits. So if we have the limit as x goes to some value a of a function f of x over a function g of x, this is equal to the limit as x goes to a of f prime of x divided by g prime of x under certain circumstances. Specifically, if it is of the form plus or minus infinity over plus or minus infinity, or 0 over 0. And those are the only times that you can use L'Hopital's rule. If it's not one of those two circumstances, you cannot use L'Hopital's rule. But the question then becomes, what about other indeterminate forms? Because there's a whole bunch of different indeterminate forms. Some of the different indeterminate forms are 0 to the 0, we have 1 to the infinity, we have infinity to the 0, we have 0 times infinity, we have infinity minus infinity, and then we have our standard ones 0 over 0 and infinity over infinity. Now, I made a video going through how you can be able to find all of these different ones depending on what sort of circumstances you are, but the general idea is that you can use, our goal is to end up with the 0 over 0 or infinity over infinity, and if you have 0 times infinity, it can turn into one of those two. Infinity minus infinity usually either turns into a 0 times infinity or just infinity times a number. You have to rearrange it a little bit. And then these three over here, all of these turn into a 0 times infinity if you use natural log on them. So let's go through a few examples and go ahead and try them and do them on your own, but we're going to go through a few examples of L'Hopital's rule. So, to start off, let's keep that in frame. So let's find the following limits. So I'll write 4 down, try them all, and then unpause the video when you're ready. So we got the limit as x goes to infinity of e to the x minus 7x. We have the limit as x goes to infinity of x cubed e to the negative x squared. We have the limit as x goes to infinity of x to the e to the negative x, and we have as x goes to 0 of e to the x minus 1 over cosine of 7x minus 1. So go ahead, pause the video, try and figure out these 4 limits, and then unpause the video when you're ready or when you would like to see how to approach these different problems. Alright, so for the first one, what we're going to need to do is we need to somehow rewrite that so it's going to be infinity over infinity or 0 over 0. But currently it's just infinity minus infinity, so we have to rewrite that one a little bit first. So let's get a little bit of space. Let's move these down a bit. Okay, so e to the x minus 7x, let's rewrite that so that we can get this as infinity times something. So what I'm going to do is I'm going to factor out one of our infinity pieces. Specifically, I'm going to factor out an x. So if I pull an x out, of the e to the x, well, that just becomes e to the x over x, and we have a minus 7. So now what we can do is now we can look to see what are each of these. Well, we have infinity, then we have infinity over infinity minus 7. So we don't know what this is yet, but that allows us to be able to do a little bit more stuff with this. So if we go through and figure out what is e to the x over x, what's that limit going to? So that means we just need to look at what is the limit as x goes to infinity of e to the x over x. Well, this is a L'Hopital rule. This is infinity over infinity, so we can use L'Hopital's rule. And we get this is the limit as x goes to infinity of e to the x over 1. So this is equal to infinity. Alright, so now that we have infinity, what we're left with is we have infinity times infinity minus 7. So all of that goes together, and that is infinity. So that is what that first limit goes to. Now let's do the second one. So we have to figure out what is the limit as x goes to infinity of x cubed e to the negative x squared. Well, this one's already as infinity times 0. So that means we just have to figure out how can I write this as infinity over infinity or 0 over 0. Well, one of the terms has a negative exponent, so let's just move that negative exponent to the bottom and make it a positive exponent. So this becomes the limit as x goes to infinity of x cubed stays on the top over e to the positive x squared is on the bottom. Now this is infinity over infinity, so we can use L'Hopital's rule. So L'Hopital's rule says that the top, we take the derivative of the top, so that becomes a 3x squared, and then the bottom, well, e to the x squared times the derivative of the top, which is a 2x. So now we can cancel an x from each term, so we can cancel that x with one of these x's. So we're left with 3x over 2e to the x squared. Well, e to the x squared, that's going to go to infinity, top goes to the infinity as well, so we need to use L'Hopital's rule again. So we get the limit as x goes to infinity, derivative of the top is just 3, and then the derivative of the bottom is going to be a 2e to the x squared times the derivative of the top, which is a 2x. Now we have a 3 over infinity. This is going to go to 3 over infinity, which all goes to 0. So that's what that one goes to. Let's do the next one. How do we do the limit as x goes to infinity of x to the e to the negative x? Because what this ends up being is this is infinity to the 0. So this is one of those indeterminate forms that takes the most work to do. So what we're going to do is we're going to say that this is equal to some value L. We don't know what it is, but it's equal to something. And then we're going to take the natural log of both sides. So we get that the natural log of the limit as x goes to infinity of x e to the negative x, that is equal to the natural log of L. Now, natural log of a limit, the natural log is a continuous function, so we can move that inside the limit. This is equal to the limit as x goes to infinity of the natural log of x to the e to the negative x. So we then have natural log of L is equal to, we can use some exponent rules with natural logs and move the e to the negative x out front. So this is equal to the limit as x goes to infinity of e to the negative x, natural log of x. And now we can see what sort of form is this in now. Well, e to the negative infinity, that goes to 0. Natural log of infinity, that goes to infinity. So we have a 0 times infinity. So we just need to rewrite that to be infinity over infinity, or 0 over 0. So this is equal to the limit as x goes to infinity of the natural log of x divided by e to the positive x. And now we can use L'Hopital's rule. And this is equal to the limit as x goes to infinity of derivative of natural log of x, that's 1 over x, derivative of the bottom, that's e to the x. So we get 0 over infinity, that goes to 0. So, does that mean that our answer is 0? No, it means that the natural log of our answer is 0. So, we just need to then solve for what L is going to be. So we know that the natural log of L is equal to 0, which means that the 0 is equal to L, so L is equal to 1. So our limit is 1. Now let's do our last one. And this one is probably the most straightforward because it's just a direct application of L'Hopital's rule. We plug in 0, we get 0 over 0. So, using L'Hopital's rule, we take the derivative of the top, and we get e to the x. Derivative of the bottom is just going to be a 7 times the derivative of cosine, which is negative sine, so negative 7 sine of 7x. So that's what we got. And we plug in 0, and we get 1 over a negative 0. Now the challenge is that getting closer to 0 from the positive side or the negative side, and it turns out it depends on which side we're approaching, so this limit actually does not exist. It approaches different things from the right and the left, and you can go ahead and check that on your own. But this limit does not exist because it goes to 0 from different sides. Okay, now that we've done a bunch of L'Hopital rule problems, let's do some optimization problems. So here is an optimization problem. We have, let's see, so we got a plane travels north at an altitude of 3 kilometers. And it's traveling at a speed of 800 kilometers an hour. Alright, so it's traveling north at an altitude of 3 kilometers at a speed of 800 kilometers an hour, and it passes over the city of Lyon, France, at noon. We have another plane that passes over at 15 minutes later. We have a second plane flies west over Lyon at the same altitude and a speed of 900 kilometers an hour. And we are trying to figure out when are the planes the closest. Okay. Go ahead, pause the video, and try and figure out what time the two planes are closest together. Alright, so the way that I would approach this is I would start by drawing some sort of diagram. So I have a plane that is traveling due north, and it is going at 800 kilometers per hour. And then we have a second plane that is 15 minutes later traveling due west. And I just realized that that is the wrong direction. So let's fix that. Okay, so it's going due north at 800 kilometers per hour. And we have a second plane traveling west at 900 kilometers per hour. So we have how fast they're moving. The question is, do we know where planes are at a certain time? Well, we know at 12:15 we can figure out exactly where they are. At 12:15 we have one plane is right there, and the other plane is right here at 15 minutes going 800 kilometers per hour. That is going to be 200 kilometers apart. So come up with some distance function, because that's what we're trying to minimize. So we can say that the distance, here let's do that in a color. So our distance d can be represented in terms of their different positions. So it's going to be equal to the square root of x squared plus, so if we just do the distance between 2 points, that is x1 minus x2 squared plus y1 minus y2 squared under square root. That's going to be our distance function. So now we just need to find equations for both of them in terms of certain times. So we probably want to have the time measured in time after noon. So that means that we want to know what are all the positions in terms of in terms of minutes after exactly noon. So our position 1, the one that's right here at this time, we can say that its position always has our x-coordinate being 0. It's just traveling straight north. So that means it's always going to be the point 0, and then its y value is going to be, let's see, minutes after noon. Here, let's just do everything in hours. So it will be 800 times t, the number of hours. And that's going to be this position here. Red one, its y-coordinate is always 0. Its x-coordinate is going to be decreasing at 900 kilometers per hour. So we have a minus 900 t. But then the challenge is we don't start at the origin. We're starting back here some distance. And how far is that? Well, that's 1/4 of 900. So that's going to be 225. So plus 225. So those are our different values, and we can plug those into our distance equation. So distance is equal to square root x1, 0, minus x2. So that becomes a 900t minus 225 squared plus y1 minus y2. y1 is 800t. y2 is 0. So we have that. And that is what we are trying to minimize. So let's just take the derivative directly. Derivative is equal to, well, we have a square root, so that's something to the 1/2. So we have a 1 over 2 times exactly that, 900t minus 225 squared plus 800t squared, multiplied by the derivative of the inside. Well, the derivative of the inside is going to be found by using the chain rule. So that's a 2 times 900t minus 225 times 900 plus 2 times 800t times 800. There we go. So that's going to be that. And so now that we have all of that, we just need to solve for when is this equal to 0? Because we are trying to minimize the distance, and so by minimizing distance, that's going to happen when the derivative is 0. So if we solve for when is this equal to 0, we only need to solve for when is the top equal to 0. So that means we just need to know when is 2 times, here, let's actually multiply a few things out. So 2 times 900, that becomes 1800 times 900t minus 225 plus 1600 times 800t. All of that is equal to 0. Let's see, let's just divide everything by 100. That'll make things a little bit easier. Actually, and then we can divide everything by 2 again. That's 9 and that's 8. Okay, so let's multiply all of that through. So that becomes 8100t minus 225 times 9. So 9 times 5, 45. Pardon me. Let's see, 18 plus 4, 22. 18 plus 2, 20. So that's 2025. It's coming up pretty soon. And then we have plus 8 times 800, that's 6400t equals 0. Solving for t, we add 8100 and 6400 together, and we get, let's see, 145. 100, yep, is equal to, t, is equal to 2025. Let's see, divide both sides by 25. Let's see, 25 goes in 200 times 81. Okay, so that is, we have 81 is equal to 140 45 times 4. 16, 18, 580. 580t equals 81. And 580 is not divisible by 3, so the best answer we got is t is equal to 81 over 580 hours. And so that is the exact time that the two planes are closest together. Alright, let's now do a Newton's method problem. Okay, so using Newton's method, find our third approximation for the 0 to y equals x cubed minus 5x plus 13 if x1 is equal to -2. Go ahead, pause the video, try and figure this one out on your own. Alright, if you don't remember, this is the formula for Newton's method. It's x sub n plus 1 is equal to x sub n minus f of xn divided by f prime of xn. So that's the formula for it. It actually comes from just the equations of lines. And so you can go ahead and try and figure that out, or you can check out this video that I made. But that's our formula, so let's go through and just do this to find our next one. So our next one is going to be x2. Well, that's going to be equal to x1 minus f of x1 divided by f prime of x1. So that's going to be equal to -2 minus f of -2 divided by f prime of -2. What is f of -2? Well, if we go through and do all of that stuff, we can figure out that this is going to be, we got -2 minus, let's see, we got -2 cubed minus 5 times -2, so that's a plus 10. Whoa. Alright, plus 10 plus 13 divided by the derivative, so we'll need that, y prime, that's 3x squared minus 5. So we are dividing by 3 times 4 minus 5, and we find out that once we evaluate that, that becomes -29/7. So we have x2. Now for x3. This is often where it gets pretty hard, and they'll probably tell you to find the first one that's hard, and then they'll stop after that, at least on a test. So x3, that's going to be x2 minus f of x2 divided by f prime of x2. So this is going to be -29/7 minus, we got -29/7 cubed minus 5 times 29, -29/7, so that's that times 5, and we have a plus 13, divided by 3 times -29/7 squared minus 5, and you'll just have to expand this fraction out, combine terms, simplify, and when you do that, you find that x3 is -53,237 divided by 15,946. That's the most simplified version, but that's going to be an approximation for the 0. Is it a pretty number? No, absolutely not. It is far from a pretty number, but that's what we would have to go through and do to be able to find these sorts of things. Hopefully the ones that they give you on the test will be slightly nicer functions, but this is the process you have to go through to do Newton's method. Alright, now that we've done this, let's talk about some antiderivatives. So I'm going to just give a whole list of antiderivatives, or functions, and you're then going to need to figure out what the antiderivatives are. So find the antiderivatives of, we got cosine x, sine x, secant squared x, 5 secant x tangent x. We got 5x to the fourth. We got 3x cubed, 1 over x, negative 2 over x cubed, 7 e to the x, x to the 2/3, and 4 plus 16x minus sine of x. Okay, pause the video, find the antiderivatives of all of these functions. Okay, the challenge with antiderivatives is keeping them straight with derivatives. So if you're completely stuck, remember antiderivatives are undoing a derivative. So the way that I do most of these is I remember what are a bunch of derivatives and then I try and undo them. So I remember that the derivative of sine is cosine and the derivative of cosine is negative sine. So derivative of sine is cosine. Oh, I have a cosine here. So that means the antiderivative is sine x plus some unknown constant. Okay? So derivative of sine is cosine. Derivative of cosine is negative sine. Here I have a positive sign, so that means its antiderivative has to be a negative cosine x to cancel out that negative. And then a plus c. Okay. What function has a derivative of secant squared? Well, that's tangent. So the antiderivative of secant squared is tangent x plus c. What function has a derivative of secant x tangent x? That's secant. So this will be a 5 secant x plus some unknown constant. 5x to the fourth, that'll just be x to the fifth. X to the 2/3. Well, the rule for taking a derivative is you decrease the power by 1. So that means the rule for antiderivatives is we increase the power by 1. So that'll be x to the 5/3. But then if we were to take the derivative of x to the 5/3, what we would get is, well, we get a 5/3 x to the 2/3. But there isn't a 5/3 out front, so we have to multiply by something that'll cancel out the 5/3, which is the 3/5. So that's how you can figure those out. So 3x cubed, what is that going to be? Well, x cubed going up 1 is x to the 4. And we still have the 3 there, but we have to divide by 4 to cancel out the 4 that will come out when we take a derivative. Okay, 1 over x. What's the antiderivative of 1 over x? What function has as its derivative 1 over x? Well, that's the natural log of x. So this is the natural log of x plus c. Technically, there's absolute values there. Okay, antiderivative negative 2 over x cubed. We'll rewrite that first as negative 2x to the minus 3. So then we increase the power of x by 1, so that'll become an x to the minus 2. When we take the derivative, a negative 2 will pop out, so we don't have anything out front. So it's x to the negative 2 plus c. 7 goes to 7x plus c, e to the x. That's e to the x plus c. 4 plus 16x minus sine x. 4 goes to a 4x. 16x goes to an 8x squared. Minus sine x goes to a plus cosine x plus c. So those are the antiderivatives of these. So practice these. Make sure that you don't get derivatives and antiderivatives mixed up. Okay, let's do some sigma notation problems. So, evaluate the following sums. We have the sum from I equals 3 to 7 of 3i minus 2. Sum from j equals 4 to 10 of j squared. Sum from k equals negative 3 to 5 of k cubed. Let's see, let's also get a little bit more. So we got the sum I equals 1 to n of 1. Sum I equals 1 to n of I. Sum from I equals 1 to n of I squared. And the sum from I equals 1 to n of I cubed. Okay. Evaluate these 7 sums. Alright, I'm going to start with these last 4, because these are ones that hopefully you have memorized. If not, I highly recommend memorizing them right now before you take the test. Sum from I equals 1 to n of 1, that's n. I equals 1 to n of I, that's n times n plus 1 divided by 2. I squared, n plus 1, 2n plus 1, divided by 6, and then I cubed, n plus 1 over 2 squared. So there you go. Those are the 4 sums that I highly recommend you just memorize. Okay, now that we've got those, how would we evaluate these sums? Well, we could try and figure out how to write them in terms of those, but all of these are finite sums. We can just evaluate what they all are. So when I is 3, we get 3 times 3 minus 2, plus 3 times 4 minus 2, plus 3 times 5 minus 2, plus 3 times 6 minus 2, plus 3 times 7 minus 2. And now we just evaluate each of these things. So that is 7 plus 10 plus 13 plus 16 plus 19. And then we just have to go through and add those up. So we got, let's see, 20, that makes 30. 16 and 19, that goes to 35. So 30 plus 35 is 65. So there's our first one. Sum from j equals 4 to 10 of j squared. That's 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared. We could add all of these up, or we could do the following. We could recognize that this is also equal to the sum from j equals 1 to 10 of j squared minus the sum j equals 1 to 3 of j squared. Well, j equals 1 to 10, that matches up with this sum right here. So we can just plug in our different values. So we got 10 plus 1 divided by 2 minus 3 times 3 plus 1 divided by 2. We evaluate that. 10 times 11 over 2, that's 55. Oh, whoops, I added up the wrong one. My mistake. That is not this one. That is this one right here. Okay, so fixing that and actually adding up the right pieces, we get this is 10 times 11 times 21 divided by 6 minus 3 times 4 times 2 times 3 plus 1, that's 7, divided by 6. So we add those up. So this time, let's see, so, and then that becomes 7, that becomes 2, okay. So we got 5 times 7 times 11. So we got 35 times 11 minus 6 times 7. 35 times 11, that's 385 minus 42. And that is all going to be 343. There's our answer. Alright, so now that we got that one, let's figure out how do we approach this last one. Sum from k equals negative 3 to 5 of k cubed. This one's a bit tricky because I equals 1 is where I cubed would have to start, but this one starts negative. So that one gets really tricky to try and figure out what do I do. So this one I would actually recommend just writing all the terms out. So you got negative 3 cubed plus negative 2 cubed plus negative 1 cubed plus 0 plus 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. Now, the interesting thing is, negative 3 cubed, that's negative 27. 3 cubed, that's positive 27. Those two cancel. 2 cubed and negative 2 cubed cancel. 1 cubed and negative 1 cubed, those cancel. So all we're left with is really those. So we just evaluate those. So that's 64 plus 125. We add those up and see what we get, and that is 189. Now that's similar to a telescoping series. I'm looking up those. There will probably be one or two of those on your test. Alright, so now that we've gotten all of these, let's move on to finding some areas. So, let's see. First one. Approximate the area under the curve x squared plus 3x plus 1 is our function f of x on the interval 1 to 7 using 6 intervals. And we want to use both right endpoints we got right endpoints, then again with left endpoints. So go ahead, pause the video, try and figure out how you would do this using our different methods, and go ahead and tackle this problem. Alright, so if we're going to approach this, we're going to need to know a few things. So before we begin, remember that the formula for the approximate area under the curve is always going to be area is equal to the sum from I equals 1 to n, where n is the number of intervals, of your height, so f of xi, delta xi's. So f of xi, this is the height of your rectangle, and then delta xi, that is the base of your rectangle. Now, most of the time we're going to want to have our delta xi's, so the bases, to be equal spaced intervals, but they don't technically have to be. But if we have 6 intervals on the interval from 1 to 7, that means that we know that our delta xi's are all going to be 1. All of those widths are going to be 1 because the overall interval is length 6. If we break it up into 6 subintervals, that means each subinterval has length 1. And then our right endpoints, those are going to tell us what are our x values. So our right endpoints, so if we were to break it up, so we have our function like this, 2, 3, 4, 5, 6. So there's our region, whatever it is. Our right, these are going to be these endpoints here. So these values are going to be 2, 3, 4, 5, 6, and 7, whereas our left endpoints are going to be the points on the other end, meaning the 1, 2, 3, 4, 5, and 6. So let's go through and figure out what these are going to be. So our right endpoints, this is going to be the sum from I equals 1 to 6. We have 6 intervals. F of our x sub i's times delta xi, which is always 1. What are our x values when we are doing our right endpoints? Well, when I is 1, our first one wants to be 2. So that means we are going to have it be f of I plus 1. Whereas our left endpoints, that's going to be the sum from I equals 1 to 6 of just f of I times 1. Okay, so now that we have this, evaluate what these are going to be. So let's move the left endpoint 1 out of the way for a second. Okay. So our right endpoint is going to be the sum from I equals 1 to 6 of f of x. let's write this down, I equals 1 to 6 f of x, so that's going to be I plus 1 squared plus 3 times I plus 1 plus 1. Now we have a couple choices. We can either evaluate this directly by computing each of these 6 terms and adding them up, or we could rewrite this in terms of all of those different sums that we were talking about just a bit ago. I'm going to just evaluate this directly. It seems like a pretty straightforward thing to do. So let's go through and see what that is. So when I is 1, we get 2 squared plus 3 times 2 plus 1. Then we got 3 squared plus 3 times 3 plus 1 plus, we got 4 squared plus 3 times 4 plus 1 plus 5 squared plus 3 times 5 plus 1 plus 6 squared plus 3 times 6 plus 1 plus 7 squared plus 3 times 7 plus 1. And if we add all of these up, let's And if we add all of those up, we get that is equal to 226. Okay, so now that we have that one, let's approximate it using our left endpoints. Now this is going to be pretty much the same thing, except instead of I plus 1 squared plus 3 times I plus 1 plus 1, this is just going to be the sum from I equals 1 to 6 of I squared plus 3I plus 1. This one is definitely one that would be a lot easier to evaluate by just breaking this up into the sum from I equals 1 to 6 of I squared plus 3 times the sum I equals 1 to 6 of I plus the sum from I equals 1 to 6 of 1. If we just add all of these up, the I squared, that becomes 6 times 6 plus 1 times 2 times 6 plus 1 divided by 6 plus a 3 times 6 plus 1 divided by 2 plus 6. We add all of these up. This is 7 times 13. So that's 91. Let's see. 3 times 3 is 9. 7 is, so 9 times 7 plus 6. We add all of those up. We got 91 plus 63 plus 6. 63 and 6, that's 69, plus 91, that becomes 160. So left endpoint goes to 160, right endpoint goes to 226. So our next question is, how would we find the exact area? Well, the exact send the number of intervals to infinity. So this would be found by looking at the limit as n goes to infinity of the sum from I equals 1 to n, f of xi, delta xi. Now the question with this is, which endpoint form should we use? Well, it turns out it doesn't matter. So let's just use our left endpoint, because in this case, that's the easiest one to just be able to just plug them in. So, but the challenge then is, what's our x sub I? Well, the formula that we're going to want to use is our right endpoint formula, actually. So we are going to want to have our delta xi's. Those are going to be b minus a over n. So in this case, that's going to be 6 over n. And then our x sub i's are going to be a plus delta xi times I. So this is going to be 1 plus 6i over n. So we go do this. This will turn into our area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of, it was an x squared, so it'll be a 1 plus 6i over n squared plus 3 times 1 plus 6i over n plus 1 times delta xi, 6 over n. So we just need to evaluate what this is. So let's go through and break this down. We got the limit as n goes to infinity of the sum from I equals 1 to n of 1 plus 6i over n squared. That turns into a 1 plus 12i over n plus 6 squared I squared over n squared, 3 plus 18i over n plus 1 times 6 over n. That doesn't have any i's in it, so we can actually pull it out front. So now that we've gotten this, let's break this down into the different terms. So we got this is equal to the limit n goes to infinity. We have a 6 over n times our I squared term. So that means we'll have a 6 squared over n squared sum I equals 1 to n of I squared plus our I term, 12 plus 18, that's 30. So we got a 30 over n. So we got 30 over n, sum I equals 1 to n of I, and we have 1, 3, and 1, that's 5, so we got plus 5, sum from I equals 1 to n of 1. Well, we know what each of these sums are, so we can say that this is equal to the limit as n goes to infinity of, we got 6 over n times 6 squared over n squared times n plus 1, 2n plus 1 divided by 6 plus 30 over n, I equals 1 to n of I, that goes to n plus 1 over 2 plus 5n. And now what we're going to have to do is we need to figure out what's this limit as n goes to infinity. Well, let's simplify a little bit first. So n 30 over 2, that leaves us with a 15 up here. Let's see, we can cancel this n with one of these n's. Okay, so now let's go through and see what this all turns into. So we got this is equal to the limit as n goes to infinity of distributing the 6 over n all the way through. That gives us 6 squared n plus 1 2n plus 1 over n squared plus 15 times 6, that's 90. So we got a 90 n plus 1 over n plus 5 times 6, that's a 30. N over n, the n's cancel. Now as n goes to infinity, we have infinity over infinity, infinity over infinity, and 30. So we could use L'Hopital's rule, or we could multiply the top and bottom by the leading or the largest power of each, and we would end up finding that most everything cancels out nicely, and we are left with a 6 squared times 2, so that's 72 plus a 90 plus a 30. So the true area is going to be all of that added together, so 102 plus 90, so the true value is 192, which our left and right endpoints were pretty close. One was a little bit bigger, one was a little bit smaller, but they are both pretty close to the right answer. So now that we've done that one, let's go through and do a bunch of other things, for example. So let's do another example of how we might be using these endpoints and stuff in a problem that you might see on your test. So we're going to have to insert a picture. Okay. Here we go. So this is an image taken from the Apollo 11 report, where they were keeping track of the velocity of the rocket at different instances. So this is going to be in the second burn phase. So this is when they were in space and then were trying to get into an orbit that would take them to the moon. So we are going to try and do the following. Approximate the distance that Apollo 11 traveled in the entire second burn phase. And so that is this entire region shown on the graph from t equals 9150 seconds to t equals 9600. So you are tasked with trying to find the approximate distance that Apollo 11 traveled in this entire phase. So from this time right here all the way to this time here. Go ahead, pause the video, and try and approximate the distance that it traveled. Alright, so now that if we have this, how would we approximate this? Well, we could use our left endpoint form, we could use our right endpoint form, or we could use both of them and average them together. That averaging together, that actually gives us the trapezoid form. We're basically forming trapezoids to approximate the area. So let's go through and try and figure out how much area we would go through. So let's break this down into a bunch of different rectangles. If we were to find the area in this little square, we're going to need to know a few things. First, how many seconds elapsed, and then second, what was our velocity at that time? Well, each of these intervals is broken up into exactly 25 seconds. So we know that our base is always going to be a 25 seconds. So now we're just going to be adding up all of the different pieces together. So we have that one, we have that one. So this is going to be left endpoint 1. So if we just go through and draw these different rectangles, we're going to be adding up all of these different heights to get our left endpoint approximation. Now, to be fair, just from looking at this, it's pretty clear that this is going to be an underestimate. We're definitely missing quite a bit of stuff, quite a bit of distance that we could have traveled as well. But, oh, that was an awful one. Alright, whatever. We'll just deal with my really crappy rectangles. Both of those are the same height. So there we go. Okay, so there we go. That is our left endpoint approximation, and now we just need to figure out how far did it travel in each of those things. Well, we can figure out, or at least estimate, what's the height at each of those points. So if we go through and do that, let's zoom out a little bit. So the different heights we're going to have, so all of them are multiplied by 25, so let's just pull that out. So then we have whatever this height is, so let's see, halfway between 76 and 80, that's 78. So 78, 78, next one's also 78. Fourth one, another halfway up, so maybe like 79. Let's see, next one's at about 80. One's at 82. Let's see, then we got 83 and a half. Then maybe 85 and a half. Let's see, this one's probably at about 87. Then we got 89. 91 and a half. And we would just continue this on and on and on. So I'm only going to use the left endpoint approximation and accept that it's an underestimate. Let's see, so we're at 91 and a half, so that's this one. Let's see, so we've gotten up through here so that I have the ability to keep track. So let's see, next one is at about 94. Then we got 96. Let's see, next one is at about 99. 102, 105, and then 108 twice. Okay, so we have all of that, and I pulled out a 100 as well. So there we go. So we got all of those different things that we just need to add up. And when we add all of those together, let's see what we get. Which is 4058,750. So they traveled over 4 million meters. And that was our underestimate. So how would we do our overestimate? How would we do our right endpoint? Well, notice this interesting thing. If we were to take everything that was here and just slide it over one spot, notice that this is now our left endpoint. If we just, our right endpoint, if we just add one little rectangle here and we ignore this first one. So let's go through and figure out what is our left endpoint one. So, sorry, I keep saying left endpoint when I mean right endpoint. Okay, so this is we currently have our left endpoint. Now let's do our right endpoint. It's going to be the exact same, except we just modify a little bit. So our right endpoints are pretty much the exact same, except we have to ignore the first one because that one didn't get counted, but then we did have to include this extra one that was here at this last one. So let's see, about how high was that one? Maybe like 107.5-ish. So we'll say that one's about there. So that means our right endpoint, instead of stopping at 108, we have one extra term at the end, plus 107.5. So if we go through and add this all up, let's see what that one's going to be. So we add all of those up, and we get this one, instead of being 4,058,750, this one is 4,132,500 meters. So somewhere between this one and the other one is the true value of how far we traveled, or the Apollo 11 astronauts traveled. But this is how we would be able to do something if we were given a graph or a table. You would do the same sort of thing. Alright, so now that we've done this, let's move on and talk about using the limit definition of the definite integral. So, using the limit definition, evaluate the integral from -1 to 1 of x cubed minus x dx, and the integral from 0 to 5 of 3x squared minus 5x plus 2. Okay, evaluate both of these using the limit definition. So remember, the limit definition says that if we have the integral from a to b of f of x dx, this is defined to be the limit as n approaches infinity of the sum from I equals 1 to n, f of xi delta x, where delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. So let's just plug this in. So we got this is the limit as n goes to infinity of the sum from I equals 1 to n of, we need to know what is xi and delta x. Delta x is going to be b minus a, so that's going to be a 2 over n. So our xi's are going to be a, -1 plus 2i over n. So that's going to be a 2i over n minus 1 cubed minus 2i over n minus 1. There you go. That's what we need to evaluate. So expand everything out and see what we get. Okay. So this is equal to, we got limit as n goes to infinity, we have a 2 over n times the sum from I equals 1 to n, 2i over n cubed, or 2i over n minus 1 cubed, that becomes a 2 cubed I cubed over n cubed, minus 3 times 2 squared I squared over n squared, plus 3 times 2i over n minus 1. Then we have a minus 2i over n plus 1 minus 1, those will cancel. So there we go. We got all of that, and now we just need to figure out what on earth is that. Well, let's break this up into a bunch of pieces and evaluate each one separately. So we got, this is the limit as n goes to infinity. We have 2 over n times, we got an 8 over n cubed, sum I equals 1 to n of I cubed. We have then a minus 3 times 4, so minus 12 over n squared, sum I equals 1 to n of I squared. Then we have 3 minus 1 times the 2i's, so that's a plus a 4 over n sum of i's from I equals 1 to n. Now, when we evaluate these, this is, we got limit n goes to infinity, we have 16 over n to the 4th times n plus 1 over 2 squared. Let's see, we need a little bit more space. Then we have minus 24 over n cubed, n plus 1, 2n plus 1 over 6. And then we have a plus 4 over n, that was multiplied by 2 over n, so that's 8 over n squared, times n plus 1 over 2. And now we just need to evaluate this as n goes to infinity. So this ends up becoming 16/4 minus, let's see, 24/6, that leaves us with a 4 on the top. 4 times 2 is 8, so that goes to a minus 8. And then a 8 over 2, that goes to a 4, and a plus 4. So we got 4 minus 8 plus 4, all of that is equal to 0. So that integral is equal to 0. Now let's do the second one. It's going to be the exact same process, and we're going to just need to go through this whole shebang all at once. So we got limit as n goes to infinity, sum I equals 1 to n of, what is our delta x in this case? In this case, it's 5 over n. And we got and our xi, those are just going to be 5i over n's. This one's a little bit nicer. So we got 3 times 5 squared I squared over n squared, minus 5 times 5i over n plus 2. So this is the limit as n goes to infinity of the sum from I equals 1 to n of, let's see, we got 5 times 5 squared, that's 125, times 3, that's 375. 375 over n cubed I squared minus 25 over n I plus 10 over n. So this goes to the limit as n goes to infinity of 375 over n cubed times n plus 1, 2n plus 1 over 6 minus Oh, whoops, that's n squared there. Okay, minus a 25 over n squared, n plus 1 over 2 plus 10. And as we evaluate this as everything goes to infinity, let's see, 6 cancels with the 375 to give us 125 and a 2 on the bottom. And that's as much simplification as we can get. So as we evaluate this, this first one ends up being 125. Then we have a minus 25 halves plus 10. So 135 minus 12.5. So that's going to be 122.5. And that is the final answer for that one. Alright, so now let's talk about how might we be able to use some other properties of definite integrals. So let's say that we know that the integral from 1 to 3 of f of x dx is equal to 7, and the integral from 1 to 3, from 3 to 1 of g of x dx is equal to 2. So let's say that we know that. Your job is to figure out what the following three integrals are. We have the integral from 1 to 3 of 2 f of x dx equals what? The integral from 1 to 3 of f of x plus g of x dx, what is that equal to? And the integral from 1 to 3 of f of x minus 4 dx, what is that equal to? Go ahead, pause the video, and calculate what each of those are. So some of the rules we can use with these, we can pull any constants out, any constants that are multiplied through. So this first one becomes 2 times the integral of f of x dx, which is going to be 2 times 7, so this one is 14. The second one, we can break them up by addition, so this becomes the integral from 1 to 3 of f of x dx plus the integral from 1 to 3 of g of x dx. Well, this first one, that one is 7, but 1 to 3 is not the same as 3 to 1. So what we have to do is we have to flip, if we flip the order the order of our bounds, we multiply by a negative. So this becomes a minus the integral from 3 to 1 of g of x dx. So this will become 7 minus 2, so this one is 5. And this last one, again, we can break this up by addition. So this becomes 1 to 3 of f of x dx minus the integral from 1 to 3 of 4 dx. So this will be 7 minus this. Well, the nice bound is we have a constant, so the constant is going to be pulled out, and then you multiply by your b minus a, which in this case is 3 minus 1. So this is going to be 7 minus 4 times 2, so this one is negative 1. We can also do a couple other things, such as using bounds. So let's say that we know that 2 is less than or equal to f of x is less than or equal to 5 everywhere. So what are the max and mins? What are the max and minimum values of the integral from 0 to 10 of f of x dx and the integral from 0 to 7 of f of x squared dx? Go ahead, pause the video, and try and figure out what those are. So the nice thing about if you know any bounds of this, that means we can replace f of x with those inequalities. So we know that the integral from 0 to 10 of f of x dx is less than or equal to 5, or the integral from 0 to 10 of 5 dx, and is greater than or equal to the integral from 0 to 10 of 2 dx. Well, we know what these outer two are, so this one is going to be 2 times 10 minus 0. So this one's 20 is less than or equal to the integral, which is less than or equal to 50, which is 5 times 10 minus 0. So the maximum and minimum values we could get are 20 and 50. But how do we do that with this one? Well, the trick with these is to recognize that f of x squared is also bounded. We know that f of x is between 5 and 2. So if we square it, it's going to be between 4 and 25. So this one is going to be between, we got 4 times 7 minus 0, less than or equal to the integral from 0 to 7. F of x squared dx is less than or equal to 25 times 7 minus 0. So it's between 28 and 7 times 25, which is 175. So it is somewhere in there. Alright, so now we're going to move on to our very last topic of the video, and that is going to be the Fundamental Theorem of Calculus. FTC, Fundamental Theorem of Calculus. Now there's two of these, so we're going to start with the first part. So this is important to remember. What does the first part of the Fundamental Theorem of Calculus say? Well, what it says is if f of x is continuous on the interval a to b, then g of x equaling the integral from x of f of t dt is continuous and differentiable on the interval a to b, and I guess I should probably put the a to b's where they belong. So it's continuous on the interval a to b and is differentiable on the open interval a to b with g prime of x equaling f of x. That's the first part of the Fundamental Theorem of Calculus. So, using that, what is g prime of x if, and now we're going to have a bunch of different things. We got first, g of x is equal to the integral from x to 3 of t squared minus 1 dt. G of x is equal to the integral from 1 to 2x of t minus sine t dt. And third, g of x is the integral from x to x cubed minus 2 of 1 plus t over 2 plus tangent of t. Okay, figure out what g prime is in each of these circumstances. Okay, so the important thing to remember is this is true specifically when it goes constant to x. This first one, that's not going constant to x, that's going x to a constant. So first, we have to rewrite that as constant to x. And if we do that, we have to change the sign out front, so that becomes negative integral of t squared minus 1 dt. And so then, now this is constant to x, so that means we can figure out what g prime is. So g prime of x is going to be negative x squared minus 1. There you go. We would do this first one. Now how about the second one? It's already constant to x, but the x isn't by itself. It's a function of x. Well, this is where we have to use the chain rule. So, chain rule says derivative is going to be function where we replace all of the t's with the top function. So it's going to be a 2x minus sine of 2x And that's what it would be if we just plugged it in, but we have to multiply then by the derivative of that top function, so times 2. So that's what g prime of x is here. Now how about this last one? This one's the trickiest one, because this isn't constant to variable or variable to a constant. This is function to function. How are we supposed to do that? Well, we're going to have to break this up. So the way we're going to do this is we are going to first rewrite that as the integral from x to a constant a of the function dt plus the integral from a to x cubed minus 2 of the function dt. So if we are to do it like this, what we're doing is we are breaking this up into 2 pieces so that we can evaluate each piece separately. And the important thing is each piece is now in a form that we can deal with. The first one we have to flip and change the sign, so let's just do that real quick. So that's a to x, a big fat negative sign out front. So now they're both constant to a function. This first one we can just go directly, so let's go ahead and do that. So we got g prime of x is equal to negative 1 plus x over 2 plus tangent of x plus, and this next one we're going to have to use the chain rule, because the t's are going to be replaced with a function, not just x. So we do that, so we got a 1 plus x cubed minus 2 over 2 plus tangent of x cubed minus 2 over, nope, there's not an over in this one. So there you go. But then we have to multiply all of that by the derivative of that function, which is a 3x squared. And that is g prime of x. So if you're doing these, remember, the chain rule comes up if it's not just x. And it has to be constant to x, not x to constant. It has to be constant to x to use it. Okay, so now that we've done this one, let's go over the second part of the Fundamental Theorem of Calculus. So the FTC Part 2. What does this one say? Well, it starts the same way. It says if f of x is continuous on the interval a to b, and big F of x is an antiderivative of f of x. Then the integral from a to b of of little f of x dx, this is equal to big F at b minus big F at a. Okay, so if we have this, I'm going to write down several integrals, and you need to figure out what they are. So here we go. We got the integral from -1 to 1 of 4x cubed dx. We have the integral from 2 to 7 of x squared minus 7x plus 5 dx. We have the integral from 0 to pi fourths of sine x dx. We have the integral from 2 natural log of 5 to 3 natural log of 3 of e to the x dx. We have the integral from 0 to 5 of sine x minus e to the x plus x squared over 7 minus 3 secant squared x dx. And last but not least, derivative with respect to x of the integral from 7 to 13 of x to the e to the 7x minus 5 minus 13x to the 17.2 plus cosine of x dx. Okay, Last 6 problems of the review. Go ahead, pause the video, and figure them out. Okay, here we go. Let's make some room to do our first 3. Okay. So this first one, integral from -1 to 1 of 4x cubed. Well, what is an antiderivative of 4x cubed? Well, one antiderivative is just x to the 4th. So we want to evaluate x to the 4th from -1 to 1. That is what this vertical bar with those values there, that's what this means. So we want to evaluate x to the 4th from -1 to 1. So this is going to be 1 to the 4th minus -1 to the 4th. Because it's f at b minus f at a. So we go top minus the bottom. So this will be 1 minus 1, which is 0. There we go. So this one is going to be a 0. How about this next one? We need an antiderivative of that, and we need to evaluate it from 2 to 7. Well, an antiderivative of x squared, that is x cubed over 3. 7x, that's a 7x squared over 2. And 5, that's a 5x. So this is going to be that evaluated at 7 minus that evaluated at 2. That's going to be 7 cubed over 3 minus 7 cubed over 2 plus 5 times 7 minus, let's see, might need a bit more space. Okay, and then we have that minus 2 cubed over 3, 7 times 2 squared over 2, plus 5 times 2. We go through and evaluate this. Let's see, something thirds minus something halves, that becomes a negative 7 cubed over 6, plus 35. And we have minus, let's see, this is 8 thirds minus 14 plus 10, so that becomes a minus 4. Combine all of those up together, and we get 35 minus 7 cubed over 6. Let's see, then plus 4 minus 8 thirds. 39 minus whatever that is. 7 cubed over 6 minus 8 over 3. Whatever that number is, that is our answer for this second one. Now how about this last one? Integral from 0 to pi fourths of sine x dx. Well, what's an antiderivative of sine x? Well, derivative of sine is cosine, derivative of cosine is negative sine. So this means this is going to be negative cosine of x, evaluated from 0 to pi fourths. So this is going to be, we got negative cosine of pi fourths minus negative cosine of 0. Well, that is going to be cosine of pi fourths, that's root 2 over 2. So we have negative root 2 over 2 minus negative 1. That's plus 1. This is 1 minus root 2 over 2. There's our answer for that one. Now let's move on to these other ones that we had over here. What are these going to be? Well, what's an antiderivative of e to the x? Well, that's just e to the x. So it's e to the x evaluated from 2 natural log of 5 to 3 natural log of 3. Well, those bounds are just fancy ways of writing natural log of 25 and natural log of 27. So this is e to the ln of 27 minus e to the ln of 25, which is 27 minus 25, which is 2. So this first one is just 2. Now how about this second one? How on earth do we evaluate this one? Well, it's going to be the exact same thing. We just have to figure out what's its antiderivative, and then we evaluate it at 0 and 5. Well, the antiderivative of each piece separately is something we can do. Antiderivative of sine, we did that one just a little bit ago, so that's negative cosine x. Antiderivative of e to the x, that's minus e to the x. X squared, that goes to a x cubed over 3 times 7, that's over 21. Antiderivative of secant squared. Well, derivative of tangent is secant squared, so that's going to just be a tangent. And then we evaluate that between 5 and 0. So this is equal to negative cosine of 5 minus e to the 5 plus 5 cubed over 21 minus 3 tangent of 5 minus negative cosine of 0, negative 1, minus e to the 0, well, that's another 1, plus 1 over 21 minus 3 tangent of 0. So that all goes to, we got 5 cubed over 21 minus cosine of 5 minus e to the 5 minus 3 tangent of 5. Let's see, so that's a minus 1, tangent of 0, that's 0, so that goes to 0. So minus 1 over 21 minus 2. There you go. That's what that one is. Doesn't really look very nice, but it is what it is. Okay, now for this last one. We need to take the derivative of all of that. Well, we might want to say, well, we have these fractions, so maybe those just cancel, and we're left with that. But that's actually not true, because that's going to be antiderivative at 13 minus some antiderivative at 7. And then we're taking the derivative of all of that. Well, what is that stuff in the middle? Well, f of 13, that's just a number. F of 7, that's just a number. So we're just taking the derivative of a number. That's a 0. So be careful with some of these. They can be a bit tricky. So that's how we would go through and do this. So hopefully this review was helpful. If it was, please check out some of the others or check out some of the videos on the topics you didn't quite understand. Feel free to check out some of my other videos, and I hope you all have a great rest of your day. Good luck on your test, and I hope to see you all again soon. Have a great day. See you later.